Now let us study the geometry of complex numbers. That is nothing but how we can graphically represent or interpret the various operations that we do on complex numbers. Now here a very useful approach is that we introduce the analogy with the vectors. That is, we know that a vector is nothing but a directed ray. Okay, so we denote a vector with some starting point, and it has an arrow pointing in some directions and which has some magnitude also. So that means if we just think of the complex plane, that is the real axis and imaginary axis, and if we think of some complex number, say z, given by a plus ib, so we know that a is nothing but the real part of the complex number and b is nothing but the imaginary part. Alright, now this complex number can be also considered as a vector starting with origin, which is nothing but number 0, and terminating at that particular point. So that means if we think of a complex number as a vector, then this is how it will look like. Now let that vector make an angle theta with the positive real axis, and let the magnitude of that vector be r. Now we know that this r is nothing but the magnitude of complex number, and that is further equal to root of a square plus b square, because it's clear from the diagram that using Pythagoras theorem we can write the magnitude is nothing but root of a square plus b square. Additionally, the angle theta is nothing but the tan inverse of b upon a, because we can see that tan theta is b upon a. But of course here, while calculating this tan inverse, we must be careful about the signs of a and b, so that we have to find the angle of the correct quadrant. So that means also as per the convention, theta must lie between minus pi to pi. Alright, so in this way we calculate that particular angle whose tan is b upon a. So this is how we represent a complex number in terms of a vector, and now we will see how this particular approach simplifies certain basic operations on the complex numbers. So first one is addition. Now here let us consider two complex numbers in general denoted by z1 and z2, and as shown here. Alright, now whenever we want to do the addition of these two complex numbers, if we translate this in terms of the vector addition, then we know that the two vectors are added using the parallelogram law. So that means we have to complete the parallelogram, as shown here, as we are familiar with this process. So the other end of that particular diagonal will represent the tip of the required vector. So that means this particular vector that we have got as the common diagonal represents nothing but z1 plus z2, right? So of course we can find out the different components of this vector also analytically, that is what is the magnitude of z1 and z2 and what is the argument, okay, that we know how to calculate. Now moving ahead, if we think of subtraction, that is suppose we want to do z1 minus z2. Now this subtraction can be viewed as nothing but addition of minus z2. So it's equivalent to adding minus z2 to z1. Now minus z2 is nothing but the z2 which is turned backwards, that is in the opposite direction. So when we take the opposite of z2, we get minus z2. Now we have to add z1 and this minus z2. So this also we complete using the same parallelogram law that we just saw. Alright, so we complete the parallelogram, and wherever it intersects from origin to that point, we draw the vector. So that will give us nothing but the resultant subtraction, that is z1 minus z2. Right. Now let's move ahead and see how we do multiplication. Now here to do the multiplication we take use of the Euler's form of the complex number. Now we know that any complex number can be written as r into e raised to I theta, where r is the magnitude and theta is the argument. Right. So let us denote z1 as r1 into e raised to I theta 1 and z2 as r2 into e raised to I theta 2. So therefore when you do the multiplication, that is z1 z2, what happens is the respective magnitudes will get multiplied. So we will have r1 r2 as one term into e raised to, now when you multiply the exponential terms, in the exponent I will come common and theta 1 will get added to theta 2 since the base e is same. So if you see, the product of two complex numbers is also a complex number in which the magnitude is the product of individual magnitudes and the argument is addition of individual arguments. So if at all we want to depict this graphically, then we will get the complex number as somewhere here, something like this. It is only approximation. So the magnitude of this particular complex number will be equal to product of r1 and r2, and the angle will be equal to theta 1 plus theta 2. So if you see, the angle of z2 is theta 2 and angle of z1 is theta 1. So therefore this full angle will be nothing but theta 1 plus theta 2. Alright. So that is the graphical interpretation of multiplication. Now based on this we can deduce how the division will behave. Now if we want z1 upon z2, that is nothing but r1 into e raised to I theta 1 whole divided by r2 into e raised to I theta 2. So therefore we can separate the magnitude part, which turns out to be r1 upon r2 multiplied by, here the indices will get subtracted. So here we'll have e raised to I into theta 1 minus theta 2. So once again, if you want to interpret this graphically, it means that it is the division of two complex numbers z1 and z2 is a complex number in which the magnitude is also the resultant of division of r1 by r2 and the argument is nothing but the subtraction of theta 1 minus theta 2. Right. So z1 and z2 are as shown here. So the subtraction will be a very small number and theta 1 minus theta 2, so it will look something like this. Alright, so it will look something like this. Since here we have seen z1 has bigger magnitude than z2, it will be a very small, and since theta 1 is less than theta 2, therefore the resultant angle will be negative. So therefore the resultant division will go into the fourth quadrant with the negative argument. Alright, so that is how we interpret the division. Now let's move ahead and see the section formulae for complex numbers. Now here also the corresponding formulae from plane coordinate geometry apply without any change. So if z is a complex number that divides the segment joining two complex numbers z1 and z2 internally in the ratio m is to n, then the complex number z is given by mz2 plus nz1 upon m plus n. Right. So here the ratio of internal division is m is to n. So you see that it's exactly the same formula. And instead of internal, if the division is external, so there also we use the similar formula, that is mz2 minus nz1 upon m minus n. Right. Now here we know that m represents the distance of z1 and z, and here n is nothing but distance between z2 and z. So the ratio of those distances is m:n. That is what is the external division. Right. Now moving on, let us see how can we calculate the angle between two lines. Now here we consider two cases. That is, sometimes we are given angle something like this, that is z1 is the common point and z2 and z3 are the two tips of those arms of the angle. Now how do we calculate this theta which lies between the two segments as shown in the figure? Now for that, what do we do is, let us first of all extend these segments backwards so that they meet the real axis. So here we show those particular segments. Now you will see that the vertically opposite angle of theta will also be equal to theta, right? Now let's consider this angle as theta 1, which is made by the segment z3 z1, and let us consider the angle made by z2 z1 as theta 2. Now it is clear from geometry that theta 1 is the exterior angle of the triangle, which has theta and theta 2 as the two remote interior angles. So therefore theta is nothing but theta 1 minus theta 2. Right. Now theta 1 is nothing but the argument of the segment z3 z1. So therefore it is nothing but the argument of z3 minus z1. Okay? Because if you look at this particular segment as a vector starting with z1 and z3, so that will be written as z3 minus z1. And similarly theta 2 is nothing but the argument of this particular vector, which is z2 minus z1. So therefore here we'll have to subtract the argument of z2 minus z1. Okay? So therefore finally we have theta as argument of, now as we know from the property of argument that if you subtract the two arguments combined, it is argument of the division. So therefore here we will have argument of z3 minus z1 whole upon z2 minus z1. Alright, so that is a formula to calculate the theta as shown here. Now we can extend this to the second case also, that is, if we are given the 4 points z1, z2, z3 and z4 as shown here, and we want to calculate the angle, we use the similar logic and derive the value of theta as nothing but is the argument of, now while writing the argument, the idea is that we should consider the angle in anti-clockwise manner. So for that we have to consider the ray which comes at the end. So therefore here the numerator would be the ray or the side corresponding to z2 minus z1, and that should get divided by the other ray or the other side, which is nothing but z4 minus z3. Alright, so this is how we calculate the angle between two lines.